Hello and welcome to another Zodian session. How about that? So today is a Thursday, if I'm not mistaken, and today we're going to continue developing our programming language called Bang, which resides for some reason in a repo called BM, and this is because it's built on top of the virtual machine called BM. You can find the source code of this thing in the description, and in the previous episode we were working on compiling loops, so you can find the previous episode in the description. We successfully managed to implement the compilation of the while loop, and today we're gonna work on something else. I suppose we're gonna try to work on compiling procedures, because right now we can only compile one single procedure, which is main. So since I'm trying to get the language to a usable state as quickly as possible, I'm taking a lot of shortcuts, and one of the shortcuts was that we can only have one procedure. So maybe today the time has come to finally get rid of that limitation. So let's take a look. Let's take a look at what we need to do in here. So I think I even have an issue for that, if I'm not mistaken. Does not support additional procedures. Yes, it is a thing in here. It is a thing. It does not support additional procedures. So let's see what we can do about that. So do I need to fetch the other stuff? I didn't think I need to fetch the other stuff. All right. So let's take a look at our example. So we have a very simple example in here, as you can see. It's a single procedure because our language supports only single procedure, and it just like loops 10 times and prints hey. We can try to run this entire thing and see if it works exactly as it's supposed to work. And there you go. It seems to be working. It seems to be working. So if you try to add another procedure in here, for instance, something like proc foo, right? There we go. And then you try to write something inside of foo, this will not compile, and it will produce a hilarious error message. Bang does not support additional procedures, only main. We are working on adding more procedures. Stay tuned. So, and that's precisely the topic of today's session, right? That's precisely the topic of today's session. We're going to be adding more procedures. We're going to be adding more procedures. That's actually quite funny. So yeah, and we can remove all of that, and if you try to run it one more time, it is working. It is working. So let's create a separate branch for this specific issue. It's going to be for 415, right? And how we're going to be doing all of that? So I think we need to find a place where we compiling all of this. So it should be located somewhere in the compiler. Right, it has to be something like compile bang module, right? So this is where we compile the module. Okay, so we're just iterating through all the top level definitions, and top level definition is basically either variable definition or a procedure definition, right? So right now we only have two top level definitions. So if you encounter a variable definition, you just compile it as it is. If you encounter a procedure definition, you look if it's main, right? You look if it's main. Then you set up the entry point for the bosom context and so on and so forth. If it's not main, you throw that error message saying that we don't have more procedures, right? We also check for the redefinition of main, so yada yada yada. So how would you... So here's an interesting thing. How would you generally compile compile a procedure, right? So let me see. So let's actually go to the drawing board, and let's imagine that you have a procedure foo, yet again, right? Which basically writes foo as before. Well, first of all, you'll probably generate some sort of a label, right? Indicating the procedure. And how do you usually enter a procedure in BM? Right, in BM we have two instructions for working with procedures. It's call and return. Right, so we can even take a look at the definitions of those instructions in bm.c. So here is the definitions of all the instructions. We have 64 of them, and if you take a look at the call, well, it's not class. Why did I type class? Call. There we go. So it's an instruction that has a single operand, right? As you can see, it has an operand, and the operand type is an instruction address, right? As far as I know, and it also produces an instruction address output, right? So this is quite interesting. So it accepts instruction address as an operand, right? And also pushes on the stack another instruction address. All right, let's take a look what's going on in here. So if you have a particular procedure somewhere here, right? So here is the procedure. And then in BM, you call foo. What is going on, right? Foo is an instruction address. So what this function will do, instruction, not function, it will take the address of the next instruction, right? It will take the address of the next instruction and push that thing onto the stack, right? All right, so ret address. So it pushes onto the stack and jumps to here, right? So it remembers where it needs to return and jumps to the particular label, to the particular address rather. Then you execute the instructions of the address, and then you can use a return instruction to return back to the original location. So what return does? It takes instruction address on the stack, right? It takes the instruction address on the stack and just jumps to it, consuming the instruction address, right? So usually a procedure in BOSM, right? A procedure in BOSM will look like this, right? Right. So you have a label that indicates the beginning of the procedure, right? Then you have an instructions, and then you have the return address, a return instruction to return back to the caller. So yeah, that's basically how it looks like. And this is what we need to compile our procedure into, right? So, but here's an interesting thing. Usually the entry point procedure doesn't look like this, right? Usually when you have something like main, right? You have the instructions of the main, right? And then instead of return, right, you're supposed to put halt, and halt is a special instruction that holds the virtual machine. So the reason why it is like that is that because there's nowhere to return. So the execution just starts from the main, and where does it return? It returns nowhere. So the only thing you can do after you're done executing your entire program is just hold the entire virtual machine. So essentially, we need to distinguish between a procedure that is a regular procedure that has to use return to return from itself, right? And also an entry point procedure that holds at the end. What's interesting is that there is more than these kind of differences between these kind of procedures. The entry point one and not entry point one. When you enter the procedure, you have the return address on the stack, and you also use the stack for other mathematical operations. So you constantly will have to keep track of, oh, okay, so I have a return address, I should not corrupt it and should not lose it, otherwise I won't be able to get back, right? And in the main, you don't need to do that because there is nowhere to return, and so that you don't, because of that, you don't have to maintain the return address. So these become two completely different procedures that have to be compiled and handled differently throughout the whole like execution, which is kind of what makes it difficult to generalize just compilation of the procedures. I have the following idea. What if we make the main just a regular procedure, right? So it's going to be a regular procedure, and essentially we're not going to set the entry point to the main. We're actually going to generate a completely separate entry point that jumps to the main, right? So, and that entry point is going to look like this, right? So it's going to be something like this. If you program in Bank, you will never actually define this entry point directly. What you will have to define, you will have to define a main procedure, and the entry point will be generated for you by the compiler. And the entry point will look like this, right? So it's going to be entry, and what you're doing here is you just call main, and after main returns from its execution, you just hold. That's it. So that way, you can compile main as a regular procedure. So you can just have a single procedure in the compiler and single process in the compiler that just compiles procedures. And the procedures look the same. They all have the return address on the stack, and they all end with the return using that return address. And the entry point just calls to that main function, and when main function returns, it just puts the halt in here. And it simplifies everything. It simplifies everything. It's beautiful. So as a matter of fact, that's precisely how C programs work on Linux specifically. On Linux, right, if you have a C program, right, if you have a C program that looks like this, let's actually write a hello world. This is going to be a hello world. This is not how you do that. Okay, so this is going to be /n, and let's recompile this entire thing. It's going to be o main.c. Okay, I didn't want to remove it, and there we go. You have a hello world. So let's actually try to compile this entire thing with the debug information and see what's going on. There we go. We now have a debug information, and I can do gdb on this entire thing, and I'm going to break on main. I'm going to run it, and let's take a look at what's going on. Okay, so we are inside of the main procedure. If you take a look at the stack, it just shows main. Okay, thank you. What if I disable all of the optimizations? Will it work? Or is that how the debug information usually generated? Right, if I take a look at BT, apparently it doesn't show that. But the point is, as far as I know, GCC and maybe other compilers first generate a start function, right? A start function, which already calls main function, right? Which already calls main function, and after main function has finished executing, it just calls the exit syscall of Linux, and it's actually kind of similar to what we're trying to do with our virtual machine. So Linux start _ start. Why does the use of start in C? Yeah. So people talking about it. It is a thing. Oh yeah, so you also, you can actually define this thing yourself, right? You can define this thing yourself, but you have to do no start files. Symbol starts is an entry point of your program. That is, the address of the symbol is the address jump to on program start. Normally the function with the name _ start is supplied by the file called crt0, yeah, I remember that, which contains the startup code, blah blah blah. It populates argv, and then it calls main, and then it calls exit. Right. If the program does not want to use croutine, you can use start. The thing about the exit, by the way, is that if you don't call exit syscall, your program is not gonna finish correctly. It's just not gonna finish correctly. Basically, the program cannot just stop executing. It needs to tell an operating system that it's done executing, so operating system can unload it from the memory, and that's what exit syscall is usually used for. And it's precisely our case, right? It's precisely our case with the virtual machine, right? Our virtual machine cannot just stop executing. It always keeps executing the next instruction. So what it needs to have a special instruction that tells the environment of the virtual machine itself that I'm done executing, that's it, stop me, unload it from memory, full stop. Right, and that's actually kind of a similar situation. So we can actually try to do that. I kind of want to try to compile this example with GCC no start files and just, you know, see what's going to happen. It's kind of interesting. All right, so I have main.c. Oh yeah, so if I try to just define something like this, right, will that even work? So it's going to be GCC no start files. Okay, so what it will see, implicit declaration of main, so that's probably means that I need to put start below the main. So what else do we have in here? Exit, implicit declaration of exit. I think exit is located somewhere in lib, stdlib, and it worked actually. It actually worked. That's kind of interesting. So if I try to execute this entire thing, it is working correctly. So here's the interesting thing. What if I don't do exit? What if I don't? Who knows what's going to happen? It will segfault. Why did it segfault? Why did it segfault? Well, because I suppose GCC compiled this as a regular procedure, since it's applied as a regular procedure, and a regular procedure ends with the return, right? But again, there's no place to return to, right? So it either tried to return to some garbage, right, to some garbage address, and it hit unmapped memory, and the operating system said, no, 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 you can do that, and killed the program completely. Or it actually continued executing after this procedure. It just depends on what exactly got generated. So if you program in assembly for Linux and you don't call the exit syscall, your program will essentially continue executing until it hits the memory that you're not supposed to touch or not supposed to execute. The operating system will just kill you with the segfault, right? That's why you need to call this exit. And usually you don't have to worry about it because this kind of code is generated for you by the compiler, right? So it's generated for you by the compiler and you don't worry about this kind of stuff. And that's precisely what I want to implement today, right? So we're going to just have a single way of compiling procedures, and then at the end of all of the compilation, we're going to generate a very small little entry point that is going to basically set up the main call and then hold the machine and so on and so forth. So yeah. So I'm just thinking, should I put any like this thing into the description? I guess I'm going to put it in the description just in case. Okay, so so you can find this thing in the description if you're interested in this kind of stuff. So let's get started, I suppose. But before we get started, I think I want to make a cup of tea. I forgot to make a cup of tea right before the stream, so let me quickly do that. All right, I'm back. Let's freaking do this. Ooh. What the fuck was that? So let's take a look at the library, bank compiler, and we probably have a procedure called compile bang proc, right? Here it is, compile bang proc. Compile bang proc. Where? Proc def. Okay, we're compiling proc definition. And essentially, after we compile the proc definition, what we're doing is, yeah, we're returning the address, and that address could be used to set up the entry point, right? Oh yeah, that's precisely what we're doing. So we're returning the address where it starts, and there we go. Everyone is happy. So essentially, after this entire thing, what I want to do is I want to do bosom push instruction, right? Push instruction bosom, and the instruction is essentially going to be the instruction is essentially going to be inst return. But I have a slight fear that it may not work properly. It just depends on what is usually going on. This one is going to be very interesting. This one is going to be very interesting. So it just depends on the return type of the expression, because if you have something like this, right? If you have a procedure bar that have something like this on the stack, this in expressions, it will push this thing onto the stack, but then that is it. Then that is it. And because of that, the return address will not be in the correct place, right? So the number just compiles to push 0, right? And that actually basically shadows the return address. So I was thinking about the word. I think word shadow is actually a pretty good word for that. So essentially we need to look at the actual value of the expressions. When we compile expressions as statements, right? When we compile expressions as statements, we need to look at whether they return something. And if they return something and we don't assign that to anything else, we have to drop it so we still have the return address on the top of the stack. So, and the question is, how can we even determine that? I guess that should only happen when we are compiling the expression as a statement, right? So let me try to find that. So it's going to be bang compile compile bang statement. Do you even have statement? Compile bang statement, stmt. Yeah, compile statement into bosom. There we go. So if doesn't return anything, variable assignment doesn't return anything, while doesn't return anything. The only thing that may potentially return something, is expression, but it just depends. It just depends, right? Because this returns something, right? Hello, right? Does not return anything. So how can we even approach that? How can we even approach that? So obviously in here, right? Obviously in here, if we know for a fact that expression is not void, right? If the expression is not void, we have to add something like bosom push instruction, bosom instruction drop, and of course this thing doesn't really accept any operands, so it can be set like that. But if is void, wait, I thought I just typed void and it incremented the void count. Okay, whatever. How can we know all of that? How can we know all of that? We can ask the compile bang expression into bosom whether it returns a void expression or not, right? But it's more of a like a type checking at this point, right? So it's more of a type checking at this point. So can we introduce the types of the expression? Or maybe it's time to introduce like yet another type called void or unit or something like that, to indicate the expressions that don't have anything, that don't return anything. Or maybe all of the expressions have to return something, but then what about functions that should not return anything, right? So yeah, you need some sort of a unit type to indicate that you don't return anything, and so you don't need to add the drop at the end of the statement. So you definitely need that. So, okay, I think this looks like a pretty straightforward way of doing that, but it feels like it has to be handled on the level of a type system, but we don't really have a type system at all, right? We have a notion of a type, but it's not really used properly as like as a type system thing. So is void, right, it's gonna be false. This one has to be not is void. And we're gonna pass is void here as this thing, right? So let me see what we're gonna have in here. So this thing is going to accept Boolean is void. So of course this entire thing is temporary, right? This entire thing is temporary, and eventually we're gonna get rid of this entire stuff, and it's gonna be handled on the level of like a type system. So bang expression into bosom. So, and yeah, we need to replace this thing, and there we go. Okay. So I know for a fact, right? I know for a fact that string literals are not void, right? And we're also going to do the following thing. If you don't care about the expression being void or not void, you can set it to null, and we're going to just be doing it like that, right? Okay, so we have a couple of hard-coded functions. So a write function is void, so I'm going to set it to true. Right, there we go. So booleans is obviously, they're obviously not void. All of that stuff is not void. I might as well actually keep copy pasting this stuff. Variable read is not void for sure. Binary operation is not void. So the only thing in here essentially that is void is a write, right? And as we actually go into supporting procedures and stuff like that, we're going to actually have more action going on is here in here, right? You see, write is sort of like an intrinsic, right? It's a function that exists in the compiler but was not defined in the source code anywhere. It's hard-coded in the compiler itself, and it returns void. And then we're gonna have custom user functions. And they also could be void or not void. So this kind of information will be useful to return from here. Okay, so let's actually try to compile this entire thing and see how it goes. This is not how we compile. How do we compile? We need to use the no build system. I'm gonna be doing just test. There we go. Okay, so in here, when I compile binary operations, oh, that's interesting. That is actually very interesting. So I do kind of care whether it's void or not. I do in fact kind of care whether it's void or not. Because if it's void, I cannot, yeah, it wants to turn into a type system. This thing wants to turn into a type system. Get fucking damn it, okay. Do I need to introduce like a proper type system so early on? Do I really need to do that just to be able to know whether I want to drop a value from the stack and not to drop the value from the stack? Maybe that's precisely what I need to do, because this thing wants to be a type system. Yeah, as you can see here, I already want to do type checking and shit like that, and it's just like, yeah, you want a type system. Okay, so let me see what we can do about the type system. Sometimes like code just wants to go its own way and there's like nothing you can do about that. The code wants a type system. Very well then. So let me see. So where do we have a types? I think we have types defined somewhere in parser. So there was a bank type and it's defined in here. There you go. So we have a bank type. And the only type in here we have is I64, right? That's the only type we have in here. So let's introduce the void type or the bottom type or like unit type. So different languages actually call it differently. So in C-like programming languages, it's void. I remember that in Scala, it was called unit type. I programmed in Scala a long time ago. My God. It's a pretty interesting language, but unfortunately it's built on top of JVM, so it's slow as fuck. Unit is a subtype of any val. There's only one value of unit, which is like nothing, like, you know, parentheses, and it's only represented by any object in the underlying runtime system. In Haskell, such type is called literally parentheses, and I don't even know if it has any name. Maybe it does. Yes, let's wait for GHCI. It's very slow on my machine for some reason. Yeah, this is the type. This is the thing in here. It's defined in tuples. Maybe it's considered like an empty tuple. Yeah, it only has the only value in here. So anyway, we need to define something. I kind of like the name unit. Could be also nothing. Oh, in Scala it's called unit because there's only one single value of that thing. All right, so we're not going to have a value for this thing. We're going to just call it void. And let's see how it goes. So we're going to have a void in here. I wonder if me adding this new enumeration will break some code. I speak a very weird English, I'm sorry. Also, I think I need to remove this is void bullshit that I added to make it properly compile, because right now it's not going to properly compile at all. All right, so it threw a warning in here somewhere, right? So bank size of type. Huh, that is very interesting. So why do you need this kind of thing? What's the size of this stuff? So we use it to push it into the address. So, oh yeah, if you define a variable of void, it needs to know the size of the type to actually push it in there. And what's going to be the size of the void? That's a pretty good question. What's going to be the size of the void? By the way, what's the size of the void in C? Is it like 1 or something? I don't know. I don't program in C. I'm not a C programmer, right? I'm a Scala programmer. Believe it or not, I actually more of a Scala programmer than a C programmer. I actually worked on commercial projects in Scala that were deployed in production, and they probably still work there. But I never did anything like that with C. So at least with Scala, I have like an actual commercial experience. So yeah, I'm not a C programmer. Like I never actually wrote a commercial thing in C. In C++ though I did, but I'm not in pure C. Okay, so let me see. Haha. So it's gonna be ZU and it's gonna be size of void, and let's see what's gonna happen. GCC main.c main, and it's 1. Interesting. C size of void. I vaguely remember something about void. What is the size of void? The void has no size. That would be compilation error for the same reason you can't do something. To my surprise, doing so actually does compile in GNU-C. We can actually do a pedantic. I think we can do a pedantic. Oh yeah. So yeah. Invalid application of size, but it failed not because of the pedantic, but maybe pedantic enabled some of these flags in here, so it's not a valid thing per se. So what about C++? What about CPP? ICPP when IP? Funny. Okay, so what do we have? Invalid. I mean, it's also throws warning. Anyway, so I think it's not that big of a deal. I think it is not that big of a deal because we can throw a compilation error when you're trying to define a variable with the void type. So this is one of the things we can do. Let me see what we can do in here. So bank size. All right. So you're trying to do type. So we're checking whether the variable already exists, and then we can check the following thing. Maybe it would make sense to actually check the type first. If var definition type is equal bang type void, we're already going to throw an error without even checking whether this variable exists or not, because that's already incorrect regardless of whether it exists or not. So we want to fail as soon as possible. Fail fast. Okay, so bang log fmt error variable svfmt, so this is the name. Okay. Defining variables with type, and we're going to provide this thing. Is there any way to get the name of the type? Is not allowed. Yeah, at least right now. I'm not sure if it's going to be allowed in the future, but we'll see. Bank log arg, and what's going to be the arg in here is going to be var def location, and now I need to know how to get the name of the type. So it's located somewhere in a parser, and do we have like really name of the type? So we have bank type. You have a procedure bank like parse bank type. So let me see, parse bank type. There we go. Okay, so it simply expects. Okay, so everything is completely hard-coded in here. So we need to introduce the static assert system, which knows the amount of types you have in there, and then if you modify the amount of times, it will break in a bunch of places. So I actually didn't introduce this kind of thing for the types. So let's do something like this: count bang types. Right. So right now we're gonna only have like two types, the two-time champion of the type system. So it's i64 and void. To be fair, in our virtual machine, you probably don't need anything else, right? And the funny thing about the void type is the only purpose of void type is to know whether you want to drop the result of the expression compiled as a statement or not, right? So if it's void, you don't have to drop anything. If you have expression which is used as a statement, you want to drop the result value. So that's the only purpose of this entire thing, which is quite interesting, which I would never actually guess that's why void would be needed for, unless I actually try to implement a programming language. So it's actually a very educational experience for me right now, right? I just like literally learned a thing in 35 minutes. That's how I learn things, by the way. I just do the thing and I just encounter some problems and I'd be like, oh, okay, that makes sense. And again, I know nothing about language development. I went to a pretty shitty university that didn't have a programming language course. Yeah, so I know nothing about this kind of stuff. So a lot of these things are just like really new for me. And that's pretty cool. That's pretty cool. I really enjoy that. Okay. So we probably want to introduce some functions. Something like void, actually not void, but bang type name is going to accept bang type and it will return your name. And then you can even iterate through all of the types and all their names, and that's how you can parse things, I think. That's one way to do that. So let's quickly implement this function and see what's gonna happen. So I'm gonna put it in here somewhere. And it would be the easiest thing to do here is to add a global table, somewhere static global table, const char, const bang type names. Right, you have a bunch of names, and this entire thing is going to be just an array, like this. Okay, okay. So this one is going to be I64, right? And this one is going to be, I guess, just void. All right. So, and of course in here we're going to do static assert, count bang types is expected to be equal to 2. The amount, okay, let's actually put this thing like this. The amount of types have changed. Please update the type name table accordingly. Thanks. Let's be polite. All right, so what we're gonna do in here. So in here, we're gonna actually basically query this type name. But on top of that, we're going to also perform a range check because C is unsafe language, so it doesn't automatically generate, range checks for you. You have to write them yourself. We're going to write them with assert. So type has to be actually greater than 0, greater or equal than 0, or less than the count bang types. And once we check everything in here, we're going to do bang type names type. There we go. And so that way we can do those things. All right, so how do we parse bang name? Parse is actually, is it compile? Why did they put that in the compiler? Wait a second. Why did they put that in the compiler? I guess it does make sense to put it in the compiler, right? I guess it does. Okay, so that means I need to go to the parser and yeah. So this is basically what I have to do in here. Bang type equal to 0, type less than count bang bang types plus type. So I'm iterating through all of the types, and if I find, so it basically expects the token, right? So but one of the things we can do in here is just basically expect a token of a particular kind. So bang token kind name. So we're expecting the name in here. This is going to be the token. There we go. And then we're going to take a look at the text of the token. Token text sv equal, and we're going to try to compare it to the bang type name, right? And we just provide the type that we got in here. But the thing is, this returns C string, and we need to convert it to SV. So I think it's something like SV from sister, right? SV from sister. And if we found the thing that is equal to this kind of stuff, we're going to return that type. So we are returning that type right away. So if we didn't find any types in here, if the name represented like incorrect type, we can throw an error in here. Fprintf std error bang log fmt, and it's going to be error invalid invalid type, and it's going to be something like S. Well, I mean it has to be SFMT, SVFMT. All right. It's gonna be bang log arg, and we're gonna use the location of the token, and then for the actual name in here we're gonna use the text of the token. Right, okay, so we reported everything correctly, and then we're gonna just exit with 1. There we go. Do we have anything else? Let's try to do no build test. Is it gonna work? Is it gonna work now? Yo, no, it doesn't work. So switch type. Okay, so we didn't handle all of the situations, so let's do case. To be fair, so maybe our code should be organized so you never try to call void on like size of on a void, but you technically will be able to if our language is going to have size of construction, right? If it's going to have a size of construction, you will inevitably will try to call size of this thing, but in that case you will have to report an error. You'll have to report an error saying that you cannot do that, and you need to know the location of where that happened. And this function doesn't know the location. So it's going to be the responsibility of the function that calls this function to actually check whether you're not trying to put a void in here. Okay, that's a good point. Let's put something like this. Void type void does not have a size, right? So bang size of type unreachable type void does not have a size. So this is how we're gonna actually approach that. So I could have just redirected to unreachable, right? But I think I want to actually handle this case specifically and tell the developer of the compiler that, well, you should never call this function on void, and before doing that, before trying to call size of a particular type, just check that this type is not a void. At least this is going to be the policy for now. We'll see how it goes. And also maybe I think I want to do something like count bang types, right, because this thing is also unreachable. All right. So let's see what else do we have in here. Okay, so here is the stuff, and I did a forky walkie, oopsie doopsie, and I wonder where exactly I did that. So this is a log fmt, and I also has to provide the type, right? Okay, compile var definition defining variables with the type is not allowed, and that's precisely what I wanted to do in here. So bang type name, actually name. And it's gonna be var def type. Maybe I have to do something like bang type. To be fair, yeah, I think this is gonna be easier because at any point I can actually add more things in here, right? And then I won't have to modify anything in here. Okay, so that makes sense. All right, so let me try to compile this entire thing and see what's gonna happen. All right, everything's compiling. That's nice. Okay, let me see what's going to happen in a runtime. So if I try to run the examples, so it's going to be examples. Let's recompile the examples. Okay, and if I run while bang ran successfully. So I want to try a couple of things now. I want to open while bang, and for instance I want to define a variable with the type void. What's going to happen? Is it going to complain? Define variables with type void is not allowed. Perfect. God damn perfect. My god. All right, so now we also probably want to do something type checkish, if you know what I mean. Maybe once you try to compile an expression, right? Once you try to compile an expression, we're going to return the type of the expression. So then this kind of stuff could be used to know whether you need to drop the value in a statement or not. So let me take a look. If I take a look at the compiler.h, so where is the expression? So bang expression, it returns instruction address, right? It returns its instruction address. And it is needed to actually facilitate compilation properly. So, but we also need to return the type of that expression, right? We also need to return the type of that expression. And the question is how we're going to return that. We can return the type of the expression like this, right? But it's probably not going to be super convenient. What if we introduce like a new entity, something like struct compiled expression, right? And the compiled expression is going to have instruction address, like where exactly it starts, and its type, right? So there we go. Yeah, sounds very interesting. So maybe that's going to be the way to go. So let's remove this thing, and this thing is going to return compiled expression. Maybe in the future compiled expression is going to have like more information about itself. For instance, like the size of instructions. We only know where the expression begins, but we don't know where it ends. Maybe that's going to be useful in the future, who knows, right? So basically compiled expression is like a chunk of code, right? It's a chunk of code and its type, right? And yeah, that's pretty much it. So what's interesting about compiled expression, if we knew its size, we could probably try to simulate the instructions and see if it leaves any values on the stack, but I don't think it's actually feasible in our case. So I'm just gonna keep it like that. So, and what's interesting is that compiled proc dev here could actually return compiled proc. Who knows? Maybe that's gonna be useful in the future, but for now I'm gonna just keep it like that. All right, so here maybe we're gonna have some sort of constructors for compiled expressions, so it's a little bit easier to make. Compiled expr is gonna accept instruction address, and bang type, and there we go. So we're gonna go to here, there we go, and might as well just return compiled expression. Address, and this one is gonna be type. There we go. Here's the compiled expression. Okay, let's actually go to the compilation errors and fix everything. Yes. So this one is supposed to return the compiled expression, right? Compiled expression. All right. This one is interesting. So it actually kind of implies that I don't need the oh yeah, I don't need the constructor, so I can just do compiled expression, and I can zero initialize it, right? Just zero initialize it, and then the result address is going to be something like this, right? And what do we have in here? So this is a string literal. This is the string address. All right, and I suppose the type of the string address right now is going to be bank type I64, right? For now, it's going to be just I64 because it's a pointer or whatnot. This one is interesting. This one is interesting because in this case, this is a type void. It's kind of, the code I'm writing right now is kind of similar to, you know, the Boolean is void thingy. And that's precisely why I got the hint that I need like a proper type system, because that's what it wants to be, because I end up writing like the same code anyway, right? So here's the type, so it's gonna be this. And for the Boolean, I'm not sure. So you know what? I think I'm gonna do in here, not here rather, but something like this. Strings don't have I don't know, a separate type. Yeah, strings don't have a separate type. Here we have I64, and this is another thing. Booleans don't have a separate type. In Bang, right? So let's actually clarify in Bang. Okay, and when you have this thing, it's going to be that. Variable read, by the way, I think it has to be void. Binary operation is rather interesting. So I think binary operation should return its type, right? So it's going to be result type equal compile binary OP into bosom. So that's how it have to work, in my opinion. All right. Okay. So we're already starting to establish like a very simple static type system, which is kind of cool. But the compile binary OP into bosom doesn't return anything. Let's actually make it return bang type. Maybe in the future is going to return a compiled expression. I don't know, but for now it's totally fine to have these things, I think. So what we're doing in here, we're just compiling left-hand side and right-hand side. So maybe the thing I can do in here is just compiled expression, compiled LHS, right? So here's a compiled LHS. And then in here, we're going to have a compiled RHS, right? So we compile them both together and I just sum them up. But before I will try to sum them up, what I'm thinking is we can actually compare their types, right? First of all, we can check if the LHS is not equal to bang type I64, we're going to throw an error about that. So essentially for now, we're going to support like these binary operations for I64s and nothing else. Yeah, I think later we can actually extend all of that. All right, if it's not equal to that, we're going to throw an error. So it's going to be std error, bang log fmt, it's going to be error. And what we're going to say in here, so we can say that plus is, let's do it like this, is only supported for type, yeah. So we're gonna say that plus is only supported for this kind of thing. So what we're gonna have in here is gonna be bang log arg compiled. So I need to do binary op LHS, and I need to extract the location of this thing, right? I need to extract the location of this expression. And I'm a little bit worried that expressions right now don't have a location. So it will be kind of sad. Because then I won't be able to actually properly report things, unfortunately. All right, let's make a small break, and after the break, we're gonna continue developing this thing. I'm back. So what do we have in here? So we need to check whether the type is the expected type, and we only support binary operations for I64 and nothing else. So I want to actually keep the error message generic and actually extract the corresponding names. Because it's going to be more readable and more portable, more copy-pastable, right? So the highly reusable code is the one that you can copy-paste, right? It's not the one that is super generic, right? And huge with a lot of interfaces. No. The actually reusable code is the one that you can copy-paste to a different place and adapt it to your situation. That's actually reusable code. So anyway. As long as supported for the type. Okay, so we need to have an ability to convert a binary operation into a name. And I think I know how to do that, right? Do we have a table for binary operations and their association with tokens. I think we had something like that, if I remember correctly. I think we had something like that. So we can basically take a binary operation, map it to its corresponding token, and then we can convert token to the name of the token and use it as the name of the operation. That's actually super cool. But I need to know where all of that is located. So I think we defined the binary operation somewhere here. So it's a binary OP kind, something like this. So that means in the parser we should have something like yep, binary OP tokens. Yes, binary OP tokens, but they're only available inside of this translation unit. And I'm thinking, what can we do in here? Can we just like, oh, I don't know, make it public? Is that a thing you can do with the arrays in C? But again, it's actually kind of dangerous, right? Because you need to do like a range checks and stuff like that. So we can introduce like a special function outside of this thing. So bang token kind binary OP bang binary OP token token, which accepts the bang binary OP, right? Binary OP actually kind, right? So this one is just a kind, right? And in here, what we're doing, we're going to check the ranges of the kind. So it's going to be kind has to be, I suppose, greater or equal than 0 and less than count bang binary OP kinds. And then we're going to return binary OP tokens with the corresponding kind. So you can take a binary operation token, convert it to the binary operator, then you can convert it to the token, and then you convert the token to the name. That's what you can do in here. All right, that looks okay. Let's actually make it public, so it's available outside in here. Something like this, right? It's available outside. And how I'm going to be using all of that? So compile binary OP. Right, compile binary OP. I'm going to take this entire stuff and I'm going to extract the token from the binary operation kind. So it's going to be binary OP kind. There we go. Binary OP kind. And then I need to convert the token into the name. So I think I will find the necessary function in Alexa. Right, bang token kind, bang token name. Where is the function token kind name? Okay, so that's precisely the function I needed in here. There we go. So we have a binary kind. We extract the token that is associated with the binary operation, and we convert it to the name that we can print in the error message. All right, so we only checked LHS, right? We only checked left-hand side, right? So now we need to do the same thing with the right-hand side. There we go. So the right-hand side, so maybe in here, I'm going to actually query replace LHS with RHS, boom, boom, and there we go. So that's basic type checking that we're doing in here. That is the basic type checking. Okay, so binary OK type. So this is the location. And then we also have to provide the type. Yeah, I almost forgot that we need to provide the type in here and also exit. Okay, so I need to focus. And the type that we're talking about here is the bang type name, and the type is essentially bang type I64, right? So that's a better version of what I'm trying to do in here. So let me copy paste it one more time. I might as well actually remove this thing, and let's just take this stuff, put in here, and rename LHS with RHS. There we go. Cool. Okay, so there is a lot of duplicate code in here, and we'll have to copy paste this code for all of the operations here. So I didn't want to extract this outside of the switch at first, but since we're having so much code, I think the time has come. I think that the time has come to actually extract this entire thing outside of the switch, even though maybe in the future we're not going to have binary operations that are just associated with a single token, but we're going to fix that when the time has come, when the time comes. Okay, so here first we compile left-hand side and we type check the left-hand side, then we compile right-hand side and we type check right-hand side. And then depending on the binary kind, right, depending on the binary kind, we're going to be pushing a different operations in here, and there we go. This is how we can simplify all of that. Okay, there's a little bit of duplicate code in here, but it's not that bad. All right, let me try to compile this entire thing and see what's going to happen. So what do we have in here? Conflicting type. This thing, yeah, this thing is supposed to return bank type, and I suppose, yeah, I can just return always bank type I64. I hope it's not gonna bite me in the ass. Yeah, it shouldn't actually. I think it shouldn't. So we just return the bank type, and binary operations always return this specific type in here. Conflicting type, so I also need to binary OP, just put it like that. There we go, there we go. And what do we have in here? Okay, so LHS doesn't have a location. Okay. All right, so apparently we do not keep track of the location of the expressions. That is very, very interesting. But the question is, should we? Should we? Because expressions, like, they have a lot of stuff, in fact. They have a lot of stuff. So we might as well just use the location of the binary operator. As far as I know, binary operator does know its own location. So we can try to do something like this, and let's see what's going to happen. Okay. So, and the same thing applies here too. So compile bang expression. So we change this function so it returns compiled expression instead of instruction address. Right, so this thing should return compiled expression. So let's actually call it condition expression. There we go. What else do we have in here? Condition expression, so condition expression address, and another one. Okay. Oh, and in here we can actually start checking things. This is actually quite cool. This is actually quite cool, because after that I can quite easily oh my god. So what if you put a void expression into while? What's gonna happen? Because void does not return anything for while to check, so it's going to be completely corrupted program that will completely like jumble your stack and shit like that. This is actually quite cool. So the program sort of tells me, yeah, you need to type check in here. Right, so let's actually do something like this, cond expression type, and if this thing is equal to, let's actually say not equal to bang type I64, right? To be fair, for now, maybe we just need to check if it's equal to void, right? std error. Okay, that's actually pretty cool. Bang log fmt error can't use void expression. Maybe we can do something like this. Expression as the condition of the while loop, right? Bang log arg, bang log arg, and the location is going to be the location of the while, right? So it's going to be log in here and void expression bang type name, and I'm going to just put this thing in here. And after that, I'm going to exit with 1. All right, is it going to work? Is it going to work now? Yo! Interestingly, it worked with while, but it had no problems with ifs. I'm actually kind of surprised. Why didn't it fail with ifs? All right, so if I try to compile if, bang if, right, so, oh, because we're skipping all of this shit. Okay, oh, that explains everything. Yeah. So then, all right, that actually makes sense. So here's the condition. We might as well try to do something like this. Compiled expression, const expression, something like this. And then we can basically check it. So compile bang while. And I'm gonna just copy paste this stuff. Can't use as expression as the condition of the if-else statement. Of if else. All right. So that's pretty cool. So we're already starting to type check things. That's nice. Oh yeah, this one had to actually be replaced. So while with if. There we go. If condition. I see. Okay. I see what happened. All right, seems to be working. Do I need to do anything else? This is actually a pretty good question. So we're type checking stuff, which is quite cool. So that means now, if I take a look at the example, right? So example looks like this. You have a while, and let's see if it still works. Examples run while bang. It only supported. Okay, this is kind of weird. First of all, we definitely broke something, right? First of all, we don't put like a new line in here, and I probably fucked up the logic somewhere there. So binary OP, right? So definitely here's the new line, and another thing I have to put in here, another new line, right? If one of these things are not equal I64, yeah, something is going to be definitely wrong. Wait a second, did I? That's the mistake. I confused var read with var assignment. That's why I put void in here. Oh my god, yes, var read is not an assignment. Assignment, as a matter of fact, is not an expression like in C in here. Right, so, but I mean, it can change at any moment. I'm just like, I'm in the middle of designing the language. So this thing, of course, has to be actually, yeah, it should actually return the type from this function. Yeah. So that will require another chain of compilation errors, like following another chain of compilation errors. So the type should be the type of the variable, but unfortunately this thing does not return that type. I suppose here we can return compiled expression, right? It's going to be compiled expression because it is in fact expression. So, and in here we can do something like this. So compiled expression result, 0 initialized, and then at the end returned like that. So, and the actual address of this thing could be just bosom program, program size and whatnot. So something like this. But the question is, what's going to be the type? The type should be the type of the global variable. Do we keep track of the type of the global variables? We don't. Look at that. We actually don't. Why don't we do that? I don't know. Bank type. We should keep track of it. So now, let's do something like this. It's going to be result type equal var type. It's actually a pointer. And we also need to go to the place where we assign the name of this variable. So we can assign the type of it as well. So let's actually go through the compilation errors. So conflicting type, right? So let's update the header file. It was var read. There we go. So this is a new var read, which returns compiled expression. What else do we have in here? conflicting type. So this one, we're gonna just extract the type. You know what? Maybe because of that compiled var thing, you should return just bank type, because we don't really care about its address. Right, so just return a bank type, and essentially, oh yeah, essentially we just don't need any of this extravaganza here. var type, and in the header, this one is gonna just return a bank type. All right, so I thought implementing procedure compilations is gonna be like a walk in the park, but apparently to properly implement procedures compilations, you need to have a very simple type system, because without that type system you cannot maintain the stack properly and know the return address. That is very interesting, right? So you need to know whether an expression has a value or doesn't have a value, so you can drop frames from the stack accordingly. This is actually quite interesting. So I love moments like that when I think one thing, but it turns out completely different. Like, yeah, no, this is not how world works. It works the other way around. Okay, so, and implementing procedures is essentially implementing a very simple type system. This is a very simple type system. So, but over time, maybe it's going to become like a basis of a more complex type system. We'll see. We'll see. So this is actually quite cool. All right, so global variable name, this one is just that. So this is not where we assign the variable, that is fine. This is where we assign it, and this is where we probably have to assign the type of it. So, and the type is located also in the variable definition. Cool. So now I could probably go to the global variable back, right, and just rename the name back to its normal. Okay, so it's gonna be that, and another one. Cool. So now we keep track of the types. Can I now run my example? Apparently I can. That is actually very cool. So yeah, here it is. Everything seems to be working. But now, what if I replace while with write test? Right, because write test is an expression. It is in fact an expression, but it returns nothing. Right, it returns nothing, so that means you cannot use it as a condition for while. Will we check that? Okay, can't use void expression as the condition in the while. Perfect. Look at that. Look at that legitness. Look at that legitness. We can even try to replace it with if, and it can't even parse it properly apparently. Expected token but got name. Huh? Isn't if actually what? Something is broken with if, with parsing of if. Expected token. Oh, maybe. Oh. Okay. Why do we have such an inconsistency here? Why if requires parentheses, but while doesn't? Okay, maybe we should fix that inconsistency. So let's actually go to the parser and, you know, change that, because that's kind of weird. Parse if bang if there we go. So yeah, I don't remember why I did that, so we can just do that. I mean, sure. There we go. So we take if, then we capture its location, of course, then we parse the condition, then we parse then, and then if else exists, we parse else as well. Okay, so I think that should be fine. I don't quite understand why it was like that. Okay, so what do we have in here? Yeah, it's fine. If I do if in here, it is also fine. Okay, so now if doesn't require any of this shit. But if I put true in here, right, it works and it executes once. Yeah. As I already said, right, as I already said, if is simply a while that executes one time. You see, while here executed was executed while this condition is true, and if is basically while but with a single iteration. Anyway, okay, so everything seems to work in here, and we have a very simple type system, which is goddamn fucking cool. I really like that. I didn't know that implementing a type system is going to be so easy. but here it is. Okay, the question is, why the fuck did we need this entire type system? Well, when you have an expression, right, when you have an expression, something like 1 plus 2 plus 3, and you compile this expression as a statement like here, right, so here is the expression, but we put it into a statement, right, you need to know the type of this expression. If the type of this expression is int I64, you then need to drop that value from the stack, because as you can see, it's not used for anything else. Right. If it's void, you don't have to do that. And that is very important, because you need to maintain the address of the return point on the top of the stack, when you reach the end of the procedure. Otherwise, you won't be able to return from that procedure. Make sense? So yeah, that's precisely why we were implementing this type system. So we know an indication, we have an indication whether do we need to drop the value or not drop the value. So yeah, makes sense to me. That's actually pretty cool. I'm learning a lot of things right now, actually. I really like that. So let's go to the compiler and let's find compile, maybe something about statement, stmt. Okay, so we're compiling a statement into the bosom, right? So if is a statement that doesn't return anything, var assignment doesn't return anything, while doesn't return anything, only expression may potentially return something. It depends on its type. So now look closer, my dear. Compiled expr, right? So here's your expr, and let's take a look at the expr type. If the expr type not equal to bang type void, we're pushing additional instructions in there. We're pushing additional instruction. So in that instruction is going to be instruction drop. So this is a special instruction that just basically drops the frame from the stack. So after compiling this entire thing, we're gonna have a single value on the stack, the value of that expression, right? And if this thing is not void, we need to drop it, right? Because this is a statement. So, and the reason why we need to support this kind of useless expressions is because you may have expressions that return something, right? Something like this, 1 plus f, that have side effects, right? So you may have a procedure f that in fact maybe returns something. We don't even support returns right now, but yeah, it may return something, but it also performs a side effect, right? So side effect. That's why you need to support this kind of thing, right? So yeah, pretty much, pretty much. Scary, scary side effects. Programmers should be afraid of side effects, row pointers. What else should be they afraid of? Assembly. All of these scary things, they should not be in a programmer toolbox, right? Otherwise, they may accidentally create something useful. All right. So let me see. So I also want to test how this entire stuff is going to work. So let's actually put word use 64, and it's going to be something like 0. So let's recompile everything. I'm pretty sure I made a oopsie doopsie. I think it should be push inst, right? Yeah, it is push inst. Push inst. Okay, again. So if I run the example while bang, it still works, but I want a simpler example. So do we have a simple example? I remember we had something like hello, right? And it's not that particularly interesting example. Let's add something like foo, right? And we're going to have an entry point in here. And now what we're going to do? We're going to do 1 plus 2 plus 3, and we'll try to see what's going to happen if you try to compile this entire stuff. So let's just try to run foo bang, and I should have actually run it from here, right? Foo bang, no statement. No statement starts with number. Okay, we can't even parse this kind of thing. Okay, so essentially we should actually look ahead into the statements, trying to identify what kind of statement that is. Right, and if we can't identify what kind of statement that is, we should try to parse it as an expression. Apparently, we're not doing it like that right now, and that's why we can't parse this. Okay, let's actually go to the parser and see what's going to happen. So, stmt, parse statement. Okay, what we're doing here, if it starts with a name, right, if it starts with a name and the name is if, we parse it as an if condition. If it's while, we parse it as that. Okay, cool. Interesting. Very, very interesting. Okay, so we only try to parse it as an expression if it starts with a name, right? Because it could be potentially a function call. Right, so because before we only had function calls as expressions that are wrapped into the statements, but now we're having any kind of expressions in a position of the statements. So that means we probably need to get rid of this entire thing in here, right? We probably need to get rid of it and just let it fall through, I suppose. Just let it fall through and try to treat it as an expression here. So here's what is going on here, by the way. So you pick into the token and you may have it as an assignment. Okay, oh, this one is interesting actually. But if it's not an assignment, I guess what we have right now is essentially do we ever reach this state? This is actually quite interesting. Do we ever reach it? Oh yeah, we never reach it. Okay, I see what's going on here. So essentially what I need to do in here is just like move this thing in here. So I was trying to parse expressions as statement. It's just like it would never reach. Yeah, it would never reach that code. It's kind of funny how C compiler never complained about that. Yeah, it's kind of strange because it was an unreachable code and it was totally fine in there. I don't know. I don't know, man. I don't know. All right, so let's try to see what's going to happen if we recompile this entire thing. Okay, so we have warning in here. Control reaches the... But it doesn't. Wait a fucking second. But it doesn't. Does it? It may potentially reach it in here. Oh, I see. I see. So you basically need to repeat this thing in here. Yeah, you basically need to repeat this thing in here, I suppose. One way to not repeat it in here is probably, again, move this thing back after here. So, okay, so it was actually not, it was actually reachable. But essentially what I need to do in here is just do nothing. Okay, this is probably an expression. Let's just fall through the entire switch construction and try to parse it as the expression. So that's basically what we're doing here. It's kind of a strange control flow, but I think maybe it's gonna work for now at least. Maybe it's gonna work for now. All right, so let me try to run the example, and it ran successfully. Right, we successfully compiled this, but it doesn't do anything, as you can see, right? Because there's no side effects. We can actually do something like this. It's going to be begin, right? It's going to be begin, and then this is going to be the end. And as you can see, it printed begin, then it performed this thing, and then it printed end. So let's actually see what it actually compiled to. Right, so we can do something like debusm, right? And here are the instructions. Yeah, you can clearly see that. So 1, 2, 3 plus I, and then drop. Yes, then drop. Okay, that's cool. If I feed this entire stuff into the right, I wonder what's gonna happen. There's no drop anymore. Yes, as you can see, there's we're pushing 1 to 3 and then we summon them up, and we're letting it go into the right without dropping it. That is precisely why we needed like a void type, so we know whether to put that drop there or not. So if I put it like this now, right, now instead of native right, we have a drop. So yeah, type system. Type systems are great, aren't they? I think they are. So that's pretty poog. That's pretty poog. So you can actually put like this. This kind of stuff could be actually executed at compile time, but we're not implementing any optimizations. Computing this thing at compile time as an optimization, as far as I know, is called constant folding. Constant folding. So at some point we're gonna actually start working on optimizations and stuff like that, and yeah, we're gonna implement constant folding. Constant folding is actually amazing, believe it or not. It's so goddamn cool. So especially if you're working with GCC and Clang are very smart. So you can take this entire code. This entire code can be compiled, can be executed at compile time completely without any problem. So let's take a look. So let's go into Godbolt. And I wonder if I can now put it inside of like main in here and get rid of this kind of stuff because it's not really needed. So let me see. Okay. Okay, so here we go. This is what it compiled to, right? So this entire thing compiled to this sequence of instructions. If I enable all of the optimizations, it got compiled to just return 4. Yes. So essentially what the compiler did, it took this entire code, and since it doesn't have any side effect, it doesn't depend on any input values, it just executed it at compile time and baked the final result into the program. So maybe at some point we're going to do a similar thing. So it would be actually kind of interesting to implement something like that. Something like this can be not only computed at compile time, it could be completely eliminated because the result of this thing is never used anywhere. So why care? So I guess, yeah, it's kind of interesting, but it's for another time. It's definitely for another time. So I'm gonna put this thing in the description if you're interested in this kind of stuff. Constant folding. There we go. There's the constant folding. Alrighty. So now we know how to drop or not drop the values of expressions that are put in a position of statements. So now we can quite safely implement a procedure compilation where you execute each individual statement, and after each individual statement, you know for sure there is no any additional stuff on the stack, and you can just jump back into the address that is on top of the stack, right? So that's precisely what we were trying to do in here. Okay, so maybe the time has come to do a committee of this entire stuff. All right. Introduce type void and dropping expression. Yeah, let's actually say introduce type void. There we go. And I'm going to push that right into the repo. Okay, I want to make a small break because I need to make a cup of tea, and after that we're going to try to implement the procedure compilation and see how it goes. Ahoy! Welcome back. So let's get this over with, I suppose. What we need is just like compile, finally implement the compilation of the procedures. So let's go to the compiler, right? So compile proc definition, right? So what we're doing in here now is we're just compiling the block. And since everything in the block is a statement, you know that after executing that block, you have nothing but the return address on this stack. We don't really have any procedure arguments. That's why we don't really care about passing arguments via the stack or memory or anything like that. So procedures right now don't have any arguments, but they're gonna have in the future. They're definitely gonna have in the future. So, but we don't have to worry about it anymore. So after the compilation of the block, essentially what we can do, we can add another instruction here. It's going to be bosom push instruction, and the instruction is going to be basically return, right? World U64.0. There we go. There we go. There we go. But now the compilation of the main instruction is completely broken, right? The compilation of the main instruction is completely broken. Without the special entry point that we talked about at the beginning of the session, it's just completely useless. It is completely useless. So what do we need to do in here? I think I want to kind of introduce a notion of compiled procedure. Right, it's similar to how we have a compiled expression that stores its instruction address and a type. I want to have a compiled procedure. And compiled procedure is going to be kind of similar to the global variable, right? Right, so we have a global variable which has its own location, memory address in address in the memory, the name, and so on and so forth. So basically, it's going to be a global variable, but procedure, right? So something like that. In the languages where the functions are first-class citizen, there is no difference between a function and a variable. Like a procedure, like our procedure, would be a variable that stores the function because functions are first-class citizens. So maybe, I don't know if we're gonna have like lambdas in here or anonymous functions or like first-class citizens functions. They're not the same things, by the way. They are completely different things. I'm sorry that I jumbled them in a single sentence. That happens from time to time. But maybe we're going to have some elements of functional programming in our language, whatever functional programming means. Because again, the problem with functional programming is the same as with the OOP. When people say functional programming, they usually mean different things. So yeah, what we're going to have in here, we're going to have a compiled procedure, compiled proc. Something like that. So this is going to be compiled proc, and what we're gonna have in here, we're gonna have a location in the file, right, in the source code. Then we're gonna have an instruction address where exactly it is located. Then we're gonna have a name, the name of the procedure, and since we don't accept any arguments in the procedures and the procedures don't return any types, I think that's gonna be it. But maybe in the future we're gonna have like a procedure type in here, the types of the arguments, because it's gonna be needed to properly call the procedure, right? And what it returns, and it's again is going to be needed to maintain the stack properly, which actually makes these two definitions kind of similar to each other, right? So maybe after all, procedure is just a function, just a variable that stores the function as a first-class citizen. Who knows? But for now, we're not going to make any assumptions, right? We're not going to make any assumptions. And another thing I want to do now, I'm going to add a list of compiled procedures into the compiler context. You see, in the compiler context, we have, you know, array of global vars and how many of them we have. So I want to have something similar. So it's going to be compiled proc, and we're going to have procs in here, right? Bank procs capacity. Let's introduce bank procs capacity, and this is going to be the size of those things. Alrighty, alrighty. So let's take this entire thing and define it in here. So, and for now it's going to be also 1024, because why not? Why not? And when you compile procedure, what we're going to be doing is we're going to be adding the compiled procedure into this list. That's precisely what we're going to be doing. All right. Makes sense to me. Makes sense to me. Let me sip my water, and we're going to quickly implement that. compiler.c. All right, so we check whether we already have an entry point. Okay, so right now this doesn't matter anymore. Right, this doesn't matter anymore because compiling procedure is not about like compiling an entry point. So let's define compiled proc. This is going to be proc, and it's going to be initialized with 0. So after that, I'm gonna point the address of the procedure at at the end of the compiled program. Then we are compiling the body, right? We're compiling the body, and then we are pushing return at the end of that body. So the rest of the things we need in here, we need a location. We can take a location from the procedure definition. There we go. And we also can take the name from here. It will be kind of interesting. Maybe the compiled proc should refer to the whole procedure definition just in case. I don't know. We'll see. We'll see. Because I end up copying a lot of things from AST to compiled version of things. So maybe the compiled versions of these things should just refer to the original AST subtrees. But I don't know. We'll see. Okay, so we initialized everything, and here I'm returning address, but I think I shouldn't return it anymore because first thing we want to do, we want to compile all of the procedures, right? We're just compiling all of the procedures, and then we try to find the procedure with the name main, and we're generating an entry point that calls to the main, and once we return from the main, it just holds the machine, right? So we don't need to return anything in here, we just need to append a compiled procedure to the list. All right, so how are we going to be doing that? So we initialized all of the 3 things in here, and maybe I'm going to just assert that procs count. So where is the procs count? So it's going to be procs count bang, I think it's a pointer, right, is less than bang procs capacity. There we go. And bang procs. I'm just thinking what's going to be in here. There we go. So, and I'm gonna just assign that proc in here and also increment it like this, and I don't have to return anything anymore. I think that is it. I'm pretty sure that is it. Let's try to compile this entire stuff and see if we have any compilation errors. There we go. So let's take a look at the header version of this thing. It has to be void now. All right, do we have anything else? Address. So has no member, compiled proc has no member address. What the fuck? Oh, because I called it inst for some reason. It has to be called address. Okay. So that's mistake on my part. Okay, so what are we doing here? So essentially, I think we shouldn't care about this kind of stuff anymore. So we just have to compile procedures. You see how we encounter a variable and we just compile the variable. Let's just take this thing and just compile it. I don't want to remove this entire code because this code contains a lot of useful error messages, so I'm going to just put it in here and we're going to reuse it a little bit later. But for now, the idea is going to be that if you encounter a procedure, you just compile a procedure. If you encounter a variable, you just compile a variable and you don't have to worry about this kind of stuff. Right. So after we compiled everything, we'll need to have a special function that generates an entry point. Right, so maybe we're gonna put it like this. So bang generate entry point. Right, so we're gonna provide bang the compiler context, then BASM into which we're generating an entry point, and then we're gonna provide the entry point name. So it's gonna be something like string view. So entry proc name. Something like this is going to be assert, and this thing is not implemented yet. So it's going to be to do is not implemented yet. There we go. Bang, BASM, and entry proc name. So, and this function is going to be public, and it could be used by the executable that performs the compilation. So essentially the executable is going to compile all of the modules into the bosom context, and then it will call generate entry point, providing the name of the procedure that is going to be the entry point. So basically the procedure that's going to be called by entry point. So that's going to be precisely what I mean. All right, so let's go into the executable, bang.c, and yeah, we don't even have to do this kind of stuff anymore. It just doesn't matter. So we even push halt in here. We don't have to do that anymore. So here's the idea. We compile module into bosom, right? We compile module into bosom, then we do bang generate entry point. We still provide bang and bosom, and the entry point is going to be main. There we go. So, and in here, I suppose this kind of stuff is going to be actually reported by generate entry point. Yeah. So in here, we can just basically do an assert and indicate that entry point got generated by bosom. So we can do that like somewhere here. All right. So first thing we do, we read the file, right? We read the file in here, then we turn the file into a stream of the tokens, then we parse the stream of tokens as a module, then we initialize the compilation context, right? So because we need to push some native functions in there, then we compile the module into the bytecode, and then we're generating the entry point for that specific bytecode. We check that the entry point was already set properly, and then we save the generated file into the file system, and of course then free all the memory that was allocated. So that's pretty cool. That's pretty cool. All right. So one thing I wanted to do in here, I need to add redefinition check to here, right? I need to add the redefinition check. Essentially, I need to have a function that gets the compiled procedure by its name, right? So it's something like a compiled proc existing proc, and it's going to be a pointer. So it's kind of similar to global variables actually. Global var. So let me, get global var by name. So here we're going to have bang get compiled proc by name. We're going to provide only bang in here and the name of the procedure, right? So the name of the procedure can be found in the procedure definition. All right. If existing proc is not equal to null, we're going to throw an error, right? We're going to throw an error. So let me see. All right. So existing proc. Procedure that is already defined. So here's the proc definition with its location, and then proc definition with its name. So you can clearly see that there is like a similarities between procedures and functions. The only difference between them is that procedures are located in the instruction memory and variables are located in the memory. Yeah, so it's kind of interesting. Yeah, there is like a symmetry between them. The first definition is located in here, and this is going to be like existing proc, and there we go. After that, if everything went okay, we're going to be doing this kind of stuff. All right, that is cool. That is cool. Let me try to compile this entire thing, and all right, so we don't have this function yet. Let's quickly implement it. This function is going to return compiled proc, and it's going to accept the compilation context and the name, right? And here is the thing. So we're going to be iterating through all of the bang procs count plus I, and if bang procs I name sv equal to the name, we're going to be instantly returning that specific proc. There we go. So I'm going to just return a pointer to that specific proc. Otherwise, I'm going to just return null. There we go. I probably need to put it into the header because it's C. You see, it is C. So I feel like we don't need this thing anymore, right? Compile expr. Yeah, we never use this thing, I'm pretty sure. It's kind of dumb. Yeah. So because of that, we don't need the redefinition anymore in here. So redefinition got consumed. So also here we're generating this kind of stuff. So yeah, none of that is needed. So I already did everything. All right, so we check for the redefinitions, which is nice. Let's see if we don't have any problems here anymore. We do have some problems. Semicolons, of course. In 2021, still semicolons problems, am I right? Okay, yeah, so this thing is not implemented yet. But can we just, we can't even debosom it, unfortunately. So we have to first implement this function. Okay, so what we're going to be doing, we need to first query the compiled procedure, right? Entry procedure. So bang get compiled proc by name. So we provide the compiler context, then entry proc name, and so let's do the following thing. If entry proc ended up equal to null, that means we couldn't find such procedure, so it couldn't be set as an entry point. So we need to report that. So it's going to be something like this. Bang lock fmt is going to be error. Could not find a procedure. The procedure svfmt to procedure. So let's put it like this: entry. You could not find the entry point procedure. Please make sure it is defined. Right, and the question is, where are we going to report that? So I said that we're going to report it at this location, but what is the location? We have no location to report it to. Well, maybe in that case, we just have to put like an error in here. Do not find the entry point procedure. Please make sure it is defined. I guess I have nothing else to say, right? We went through the entire source code. We compiled everything, but we couldn't find the main procedure. So there's no place for us to report this to. So we just couldn't find anything. So it's just going to be a general error, right? Makes sense to me. Anyway, so after we've got the procedure, we know its address. So what we're going to be doing, we're going to set, we're going to actually remember an instruction address, entry point address, and the entry point address is equal to the end of the program. We're going to be generating the entry point at the end of the program. So it's going to be program size. There we go. So this is the entry point address. After that, I'm going to set the entry as the entry point address, and then I'm going to say that, okay, the entry point has been generated. So it's going to be true. Might as well maybe even inline this entire stuff, because why not? That kind of makes sense. Right, so here's the entry, here's the entry, like indication that entry was set. So, and let's start generating instructions. First instruction that we want to generate for the entry point is going to be call to the entry procedure. Right, let's quickly do that. Bosom instruction push, I think it's a push instruction. Right, it's going to be bosom instruction call, and we're jumping to entry procedure address. And this is a pointer, right? This is a pointer, so we have to do something like this, right? So this is the first thing we do in the entry point. The second thing we do is simply halting. So it's going to be halt. There we go. So we just generated an entry point. Is it not cool? Is it not cool? Well, I think it's pretty fucking cool, mate. I think it's pretty fucking cool. All right. So let's see what's going to happen. Boom, boom, boom. I need to recompile the entire stuff. So did I fuck it up yet again? So what does it say? Yes. Okay, so I have to do something like svarg entry proc name. Anything else? So is it a push instruction? Too few arguments. Oh yeah, this one has to be like word use64 0. There we go. All right. So if I try to run the disassembly of the example, this is what we got. All right. Let's take a look at the example itself. Foo bank. So it basically does a useless expression 1 + 2 + 3 + 4. And this is what we got generated. So this is the entry point. And in the entry point, we're jumping to the address 0. So 0 is somewhere here, right? And here we sum up everything. And since this entire thing is not void, we're dropping it. And then we're returning back into the entry point, and entry point just halts it. Perfect. Actually perfect. And here's another thing. What if I add another procedure in here? Let's actually put another procedure. Will that work? So it's going to be something like write foo. Write foo. And I think it worked. As you can see now, the entry point jumps not to 0, but actually to 4. 0, 1, 2, 4. Which is kind of... that is really, really sus. 0, 1, 2, 3. My brain is already shutting down. I'm sorry. I skipped 3 because I should work at Valve, by the way. Yeah, I'm already a little bit tired, but yeah. So here's the foo, which basically like prints the foo text, and this one is main. So we jump to main. And we never actually do anything with foo. And the reason why we never actually do anything with foo is because we don't know how to call procedures. Yes. This needs to be implemented separately. Yes. As I already said in the previous streams, if you want to be able to have variables, you need to code defining a variable separately, reading the variable separately, and assigning variables separately. These 3 things, defining variable, reading, and writing, are 3 separate processes that has to be coded explicitly separately. The same goes to the procedures. Defining procedures is one thing, executing procedures is second thing, and calling procedures is the third thing, right? So we can't call these procedures. We can compile them, but we can't call them at all. So let's try to compile the while example and see what it gets compiled to. Looks pretty reasonable. So here is the entry point, right? We jump to the 0, and yeah, at some point we return from this entire thing and we halt. So let's actually test how it works. Let's test how it works and see if it doesn't introduce any errors. And as you can see, it worked fine and it exited fine. It didn't like stack underflow or stack overflow. It returned fine. So that's actually pretty cool. That is in fact pretty cool. Let's try to redefine foo and see what's gonna happen. I have to switch to foo. Yeah, there we go. The procedure foo is already defined. It was defined here, as you can see. We can define bar. We can just define bar, and this one is going to be simply bar. Right. Cool. That is cool. That is cool. All right. I wonder how much time it will take to implement function calls. You may say that we already have function calls, but we basically hard-coded a single function called write. But it would be kind of cool to be able to do something like this, foo. Then inside of the foo, right, inside of the foo, you would do something like foo and then bar, and just see how it just chains together and returns appropriately. So, but for now, you won't be able to do that. It is not a thing that you can easily do. You can't even parse that because our functions are hard-coded to be like that. To be fair, we can do the following thing quite easily. In the parser, right, so parse bang proc, is it proc call? But something about calls. Fun call. Yeah, it is called fun call. And what we're doing here, we expect open paren, Right, and then we parse the expression and expect close pattern, which is rather interesting. So can we do the following thing? Right, if so we need to look into the next token. How can we look into the next token? So let's allocate a bang token. It's going to be 0 initialized, and let's peek into the next token. If Lexa, it has to be bang Lexa peek. We provide the Lexa and the pointer to the token, and we say let's actually peek into the next one, into the current one. Right, if you do have the next token and that token is equal to this one, right, is equal to this one, so it's going to be token kind equal to that, that means you don't have any arguments. So in that case, I suppose you can quite safely just return null, right? You don't have any arguments in here, right? So you expect token open parent, that removes the parent. Then you look into the next token, and if it is closed token, you can try to materialize it, right? By just basically, you know, doing next in here, like this, and just return null, indicating that, oh, okay, you don't have any functional arguments, right? If you do have something in there, something else, you should try to parse it as an expression and then just return it like that. So now this way we support function calls with 0 or 1 argument. So yeah, we even have an issue for that, but I think we can quickly hack it together like this. So since we can't have procedure definitions with several arguments, it doesn't really matter. It doesn't really matter at all. Okay, so let's try to run this entire thing. And what about foo? Okay, unknown function bar. Okay, so we passed the parsing stage. Now we're trying to compile the functions. Can we quickly do that? How hard would it be, actually? Just think about it. So unknown. Okay, so if you encounter an unknown function, we can quite easily just query it. So it's going to be compiled procedure, right? So it's going to be proc bang get compiled procedure by name. We know the name. The name is expression as function call name, right? So something like that, all right? And if procedure is equal to null, only then we're gonna complain that it's unknown, right? If it is known, we can just call to that function. I mean, why not? Bosom push instruction, bosom instruction call, and the operand is gonna be word u64 procedure address. That's it. Why can't you do that? It's as simple as that. So, and on top of that, you have to actually return the void type, right? So because to indicate that you don't have to drop any results from there. All right, so if I try to run this entire, not really run, but compile this entire stuff, maybe we're gonna have function calls. So bang get procedure by name. I also have to provide the context, of course. Thank you very much, compiler, for reminding me about this kind of thing. This is a pointer. Thank you very much, compiler. I really appreciate that. And do we have anything else? Okay, let's try to do the following thing. I'm gonna disassemble the foo example, and what do we get? We have a bunch of calls, to be fair. We have a bunch of calls, which don't really make much sense. You call to 9. All right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, then you go to 4. You push 4, 4, you write, and then you call 0. All right, here you write something and you return, and okay. Looks reasonable. Yeah, we have 3 functions. We have 3 functions in here. Let's see. And we have 3 calls. Here's 3 calls. And I suppose 3 returns. That is pretty cool. Is it gonna work? So if you take a look at this code, what it should do, it calls foo, foo writes foo to the standard output, then calls bar, bar writes bar and returns, everything returns and just exits. We can also put something like write end at the end of this entire thing, right? And let's just disassembly. Yeah, there we go. So we're taking that into account. And let's just try to run this entire stuff. It works. It printed foo, bar, and end. So theoretically, we can have a recursion. But I guess we're going to explore the recursion a little bit later. I think it would make sense if we had arguments, right? So maybe if we had arguments, we could implement something like Fibonacci number calculation or something like that. But yeah, we managed today implement procedure compilation, function calls, and simple type system that supports two types, i64 and void, and use that type system to know whether we need to drop the values from the stack or not. That is goddamn fucking cool. I really like that. So yeah, today was a pretty productive stream. I didn't expect to actually manage to implement that, but yeah. So we can even compile this kind of shit. That's pretty pogue. That's pretty pogue. So we need to think about maybe thumbnail. I'm thinking, can you actually do a recursive shit with that? Right, can you do a recursive shit? You should be able to do a recursive shit. Yeah, let's give it a try. So it's going to be something like main, and it will obviously overflow the stack. Right, it will obviously overflow the stack, but let's actually see. Unknown function main. Oh shit! Oh fuck, you can't have a recursion yet. Nice, I love that. Can we quickly hack it together so we can have a recursion? So essentially, when I compile proc definition into bosom, right, I compile in a block. Can I append? Because I already know the address. I literally know everything before I try to compile the block. I literally know everything, which means I can just put it like that. All right, so I know where it starts, I know its name, I know its address. And while I'm compiling this entire thing, it will be already in the procedure. So that means I should be able to do this thing. Unknown, well, I mean, I need to recompile this entire stuff, of course. Come on, there we go. So, and there we go, it compiled successfully. So as you can see, we jump to 0, and we keep calling 0, never actually exiting it or anything. So we have a return, but it's unreachable. We have a hold, but it's unreachable. So, and if you try to run this entire thing, right, if you just try to run it, it will stack overflow, right? It overflew the entire stack of the virtual machine, which is quite expectable. Which in fact, quite expectable. And you know what? I think this is a pretty goddamn good thumbnail. Not gonna lie. So this is gonna be the thumbnail of today's stream, right? What procedures compile to? Oh, anyway, thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow, by the way, Friday, and that means tomorrow we're gonna be picking a random one-off topic, and it's not gonna be any of the of my projects. It's gonna be something completely new, and we're gonna do that for the whole session. I have a list of different ideas to try out, to check out, and I think it's gonna be interesting. So thanks everyone for watching. Love you.